Carandini here for the fourth Heller lecture, what we call the more popular one. And today we host a new speaker, Matteo Carandini, for a seminar, a scientific seminar. And we are really proud to have you, as I said on Tuesday. We know that you already enjoyed your visit here from talking to you. We gave Matteo a real hard schedule, and he completed it very successfully. So
thank you very much.
And thank you.
Thanks for having me. How is the volume? Is it okay back there? Okay. So the hospitality has been fantastic, but I feel a little bit like, you know, you go and have a wonderful dinner at somebody's home, and then you show up again 2 days later. You feel a little guilty. So I feel really guilty now to take again another hour of your time. And I'll try to stick to an hour for sure. At least that's what I can promise. So today So 2 days ago I gave a talk that was kind of general, and also when we talked about groups of neurons, I barely ever said what they do. I just said these neurons like to fire together, this neuron likes to be a soloist, this neuron likes to be a chorister, these neurons maybe form a clique, but I didn't say anything about what these neurons do. And so this talk is not about the same neurons, but it's about actually trying to understand what neurons do, which is kind of like much more traditional, and it's certainly my tradition. So I'll start with an introductory part that goes through the visual system and my experiences with it. So the early visual system, roughly speaking, includes the eye, the lateral genicular nucleus, and the primary visual cortex. This is a section through a monkey brain, and none of the work that I'll tell you about is done in monkey. In the beginning it's done in cat, and the rest is done in mouse. But the monkey is more beautiful to look at. And so when I started, and I had my own lab, in '98 I started having my own lab. I had a plan, which was to make a model, something like this, I'll explain this in a second, that would start from images and would produce firing rates of neurons in lateral genicular nucleus, and that would work with arbitrary images. And it would have to work on images, because otherwise, as my friend Eero Simoncelli taught me, if a model of vision doesn't work on images, it's not a model of vision. And I thought this is going to take just a little bit, and then I'll move on to V1, where my real interests are. And this started in '98, and the last papers we published was in 2008. This took 10 years. And I lost all my hair. No, I mean, I was already bald, but still, it was way more work than I ever thought. So then I kind of changed plans. So I want to spend a few slides, two slides, telling you about this work, and then telling you why I actually changed tack. So the summary of about 10 years of work is that we came up with this very simple model that basically summarized what was already in the literature, but we kind of made it work, that says that you have images coming in, you have receptive fields. This doesn't look at all like a receptive field, probably, to you, but if you think about this as space and this as time, you're thinking about a center surround receptive field that has a temporal impulse response. I'm sorry if this is esoteric, it's not going to matter for the rest of the talk. And then if you think about the neuron having a receptive field and then having some kind of mechanism that controls responsiveness based on luminance, in the actual model, this arrow comes from the image. And then you imagine some other stage that controls responsiveness based on contrast, and this arrow actually comes from other neurons that also look at the image, and then you add some noise. You have a very simple model, and I know that I didn't really fully explain it. I'm going quickly, but this is just background. And then what we did is we constrained all the parameters of the model with simple stimuli such as gratings. For example, gratings that were drifting in front of the eye with different contrast or different luminance or different combinations of contrast and diameter. And we obtained impulse responses, which I'm not even telling you how we obtained them. These are, you can think of them as the responses to a little impulse of grating. And we measured them. I think the measured ones are in black and the model ones are in red. But I might be the other way around, I don't remember. But the fact is that black and red are very similar to each other. And so this model did a good job at predicting the responses to these gratings, although the word prediction here is wrong because these are fitted, right? Then we froze the parameters. We allowed only one parameter still to change, which was an overall responsiveness, because you have to do that. And then we challenged this model with a natural stimulus. And this is a natural stimulus, which is a movie taken from the head of a cat. It's called the cat cam. And basically, let me show it to you. Well, first of all, the movie is taken from the head of a cat that is walking around the forest in Zurich. But the spikes are measured from an anesthetized cat, a neuron in LGN, that has a receptive field centered on the screen. So let me just give it to you again, just for flavor, okay? And we tested the model with lots of movies of this kind and movies that are more artificial, because in natural movies, nothing really moves by itself. Everything moves coherently because the cat is moving its head, okay? And so then nothing in this model could change, and we measured the actual firing rates, which are in gray, and the predictions of the model, which are in black. It's not perfect. How good is it? We could explain about 60% of the variance. I think this particular neuron, we had way more data for this neuron, is shown in red. And so we could explain about 60% of the variance for natural movies versus about 80% of the variance for gratings. Now, this is a pessimistic view, though, right? Because this was fitted and this instead was frozen. So chances are that if you fitted a model also including this, you could do better. And also, I'm sure you could do better if you added some elements, for example, a spike generating mechanism that has a refractory period. We didn't put it in. So I'm sure that one could do better. But it took 10 years of life to get to this point. And the question is it good enough or not? Oh, by the way, I'm telling you that this is what the LGN does. Well, this is what X-type cells in the LGN of a cat do. That doesn't mean that we understand every type of LGN cell and every type of retinal ganglion cells. There's many different kinds of retinal ganglion cells. So I'm not saying that the problem of the retina and the LGN is solved to 60 or 80%. I'm saying, though, that very simple models that include notions that have been around since the 1940s, I would say, most of them, but just done properly, gets you to 60 to 80% of what the eye and LGN does, okay? Yes?
The activity of the neurons now, does it affect the explanation of the model in 100 milliseconds ahead and so on?
So is there some? Okay. So this is actually something we tested experimentally, and the answer is no. We didn't put it in the model because it's not in the data. And the reason and the way we tested it experimentally was to record the responses to a whole movie and record the responses to only a half movie that was preceded by a gray screen. And these responses are identical. If you did this in visual cortex, it would be completely different. Okay, it would make a huge difference whether you are preceded by stimulation or not. But anyway, I just want to say though that one could go on along this pathway and go back to V1 and use all sorts of models. And we did a little bit of it. Well, the summary here is that responses in lateral genicular nucleus can be predicted fairly well, 80% for grating, 60% for natural stimuli, by simple linear filtering, a receptive field, and gain control mechanisms that operate on images. I mean, you could follow this pathway and go to primary visual cortex and try to do a similar job. And I just want to give you one slide of, again, many years of work in which we recorded from about 100 electrodes, 96 electrodes in the cortex of a cat, primary visual cortex. We first did optical imaging. So each electrode landed in a place that prefers a different orientation. And then we presented stimuli that had one of two orientations. They could be vertical or they could be horizontal, and they could have different contrasts, and they could be on top of each other. And then we recorded the population activity to each of these stimuli. So this is the activity of neurons tuned to various orientations in response to a vertical stimulus. And so, just to give you it's a very basic statement. When you show a vertical stimulus, the neurons that like vertical fire a lot. The neurons that like horizontal don't fire. When you show horizontal, the opposite happens. Now, what was interesting to us, and this is just to give you an example, was what happens when you sum two stimuli, each of which gives you a very nice response. For example, take this 12% horizontal grating. It gives you a very nice response in the neurons that like horizontal. Take this 50% vertical grating. It gives you a very nice response in the neurons that prefer vertical. When you sum them together, you look at the population response, look at the dots, not at the curve. You will find that this response looks very similar to this one, as if there was no horizontal grating, right? You should see the sum of this bump and this bump, but you only see one bump. There's this ferocious competition, and this is what we were studying and measuring. And just to give you an idea, you can still have a model that predicts that. In this case, it's a normalization model that says that the response to stimulus 1 plus stimulus 2, when the two stimuli have two different contrasts, is given by basically a weighted sum of these two Gaussians, one that is here and one that is there, divided by some overall measure of overall contrast, root mean square contrast, and that's what creates the competition. Okay? Okay, and it's a combination of the exponents and the denominator that creates the competition. Again, I'm going fast because all I want to say is that you could, in principle, try to follow this approach and say, okay, I'm going to start with gratings, I'm going to write equations, and I'm going to predict responses, and then I'm going to make the stimuli more and more complicated, and until they're natural images, and then I will predict what V1 does. I think this would be really, really hard, but in principle it's doable. But I want to give you a reason why instead my line of research took a 90-degree turn and didn't go there. Okay? And the reason is shown here. If you show the same movie, I don't even know what the movie is, I forgot, 25 seconds of movie. You show the same movie 3 times, and you record from a neuron in LGN, you get 3 times a firing rate that is very, very similar. It's hard for you to see that there are 3 curves here. If you do the same thing, you show 3 times the same movie, and you record from a neuron in V1, you get 3 very, very different curves. This is an anesthetized cat. And it's a point that I will make explicit in a few slides. So of course, if you were to repeat it 10 times, 20 times, you would get some very beautiful firing rates that would tell you what is it about the visual stimulus that this neuron liked. But intuitively, there's something else that is determining the responses of V1 that is not vision. Okay? Okay. So you can quantify this by measuring mean versus variance. Here it's done in spikes per second, which is silly. Should have been spike counts, but it's the same thing. And then you find that the ratio of variance to mean tends to. Sorry. So this is for this particular neuron in LGN and this particular neuron in V1. This is responses to different stimuli. You notice that they have very similar means, but very different variances. And if you now do this for lots of neurons, you find that the distribution of variance to mean, which is called here variability index, is much lower in the LGN than in V1. So there's something fundamentally different happening in cortex that is not happening in LGN, and which makes you think, should I really be studying vision to that detail, or can I spend my few left years of research some other way that is maybe more, I don't know, innovative? And so let's look again at these responses of a neuron in cat V1 to 1, 2, 3, 4, 5 presentations of the same stimulus, which lasted 6 seconds. As I told you, these 5 responses are very different from each other. And if this neuron was simply doing vision, they should be identical. And they should look like this. And this is simply the average across, 20 presentations. Okay? And so the difference between what you actually record and what the neuron should have done if it was doing purely vision is, you can call it noise. I am the great-grandchild in terms of PhDs of Lord Adrian, and Lord Adrian would have said this is noise because he would have given the same stimulus and obtained the firing rate, and if it wasn't the same, he would have said it's noise because this stuff is sensory. But let's see if it's real noise and what properties this noise has. And one way to study it is to record not just from that neuron, but also from those other 96 electrodes around that neuron, right? From a population to which this neuron belongs. If you use as regressors, and you can cross-validate to know that you're not overfitting, the activity of these neurons in response to the stimulus, suddenly your predictions of the activity of this neuron become very, very good. So I'm going to go back. This is how bad. So black is the actual response of the neuron. Gray is what should have seen based on vision. And now with red, you get the prediction based not only on vision, but also on the activity of the population. And it's just a linear model, nothing else. Now you can explain a lot of what that neuron does, which means this variability is shared. It's not the noise of an individual neuron that sometimes likes to spike 10 times and sometimes likes to spike 5 times because it's a noisy machine. Okay, so let's quantify how much better do we do at predicting the activity of this neuron if we know this population. And the answer is we do tremendously better. Okay? These dots correspond to multi-unit activity, and these dots correspond to single, well-isolated spikes. And then we're talking about recordings here. Okay, here we always have multi-unit activity. And
This with the whole population activity or just the average?
oh no. Each electrode is allowed a weight. Okay, so let's take these. Well, let's take this dot because this dot is the example that I showed you before. So, based on the stimulus alone, you could predict 18%, say, of the variance of what that neuron was doing. You could tell that it was pretty pathetic, right? Once you take into consideration the population, now you can explain 60%. And if you do with multi-unit activity, it's even more impressive. So roughly speaking, if your job was to predict what this neuron does, I think it would be better to concentrate on this side, which gives you this much, than to concentrate on this side, which only gives you that much. Okay? So this is why I made this change. Not that I'm not interested in vision anymore, but I'm interested in what else is happening. So the summary here is that V1 responses are highly variable. To predict them, one needs the non-visual activity of other neurons, which varies across trials.
But why stand? What do you say stand?
Because if it was visual, given that the visual stimulus is always the same, the response should have been always the same.
So it could be noise. Non-visual could be noise or shared.
But shared, yes. Okay. So the next question was this. Let's call it noise for still another slide if you want, but then we'll stop calling it noise. Is this noise that is shared, is it additive or is it multiplicative? And the reason why I ask is that typically when you define noise is you take some responses, you take your expectation of them or their average, you take the difference, you measure the size of the difference, and you call that noise. And so intuitively, typically people think of noise as being additive. But there have been studies who propose that the noise could be multiplicative. And let me just go back and tell you one way in which it could be multiplicative. It could be multiplicative, for example, if this denominator was noisy. In one, for a few tens of milliseconds, it's a certain number. Maybe this term, which is a constant in principle. Maybe it's not a constant. Maybe it changes with time, and maybe it provides noise, right? It will be a multiplicative effect on the responses. So there's possibilities for noise to be multiplicative and possibilities for noise to be additive. So we did a study, which I'm summarizing with one slide, in which we said, well, let's imagine that we have a neuron, C, and it has a tuning that depends on the cell, C, and the stimulus, S. I don't know why the quality is so low, I'm sorry. And so if there was no noise, we would be done. We would just get spike counts. But imagine that there's also some global activity in the population or in a wider aspect of the brain, but a wider region, which is different on each trial. And let's imagine two possibilities for this variability and its interactions with the visual responses. One possibility is that it's additive, the interaction, so there is an additive offset that changes in the whole population, and each neuron is allowed to give it a weight, okay? And another possibility is that the interaction is multiplicative. There is a gain factor that tells all the neurons, be 15% more responsive now, be 10% less responsive now, and this is a multiplicative factor. And what we found is that you need both of these to account for the data. So if you only had the additive one, you would, quality index is a complicated thing that I won't define, but it's in the paper. You do a better fit with cross-validation if you have an affine model, that is a model that is both additive and multiplicative, than if you have a purely additive model or a purely multiplicative model. So we can still think of it as noise, but it's noise that has some you can start defining mathematically what it does to your responses. It adds an offset, and it also scales the responses. If you think of them as a tuning, as what it does to tuning curves, even though you can't ever measure a tuning curve in one instant, you can think of it as going up and down and getting taller and shorter. Okay, so I'm going to get to Hein's point, which is there's some kind of interaction between stimuli flowing to neurons and populations and to the whole brain, and signals that go from the brain to the population to the neuron. But we can't really study this stuff because we're in an anesthetized cat. So we have no idea what's happening in the brain. We're trying to keep it as sleepy as possible so the cat doesn't wake up. So we had to change species, and we had to move closer to human if possible. And so we chose the mouse, which is 10 million years closer to us, as I think I said 2 days ago, I don't remember, than the cat. Did you know that? That cats and dogs are more distant relatives to us by 10 million years. So we're talking about 75 million years, so 85 million years of distance with our last common ancestor with cats and dogs, and 75 million years of distance with these guys. So they're family, okay? And so there you can actually measure behavior, and you can control behavior. You can train them to do stuff, and you can really study the way the activity flows. I hesitate to say information because that is a loaded term, but you know, things flow both ways. Okay, so now I'm going to give you a few examples of the kind of work that we're doing with this kind of approach. I showed this video 2 days ago without saying at all why we were doing it. Here's a mouse that is looking at visual stimuli, and as it's looking at visual stimuli, it's walking on a ball because it feels like walking. Nobody's telling it to walk. And there's no relationship whatsoever for now between what's on the screen and what the animal does. But one thing I want you to notice is that sometimes these gratings are large and sometimes they're small. And they're always centered on the receptive fields that we're recording with these electrodes in V1 of the mouse. Now I'm going to jump straight to something we discovered, but there's lots of things we didn't discover, okay? That they were as expected. So I'll tell you the one thing that was unexpected. The one thing that was unexpected was how the relationship between stimulus size and firing rate was affected by running. I need to take two detours. The first detour is to bring you back to the top level. Why do I now have a mouse running on a ball? We were talking about vision, right? The reason I do is, number one, in recent years it has been shown that when a mouse runs, the activity in primary visual cortex is elevated. This was discovered by Stryker, and Neil Stryker. And Neil Stryker proposed that it was purely a gain change. The neurons would fire more or less, but their tuning properties would not change. So that's what we were testing here. And more generally, we're looking for non-visual effects in visual cortex, right? Okay. So the other thing I want to remind you of is that these kind of curves, they're called size tuning or surround suppression, is something that is very commonly measured in visual neuroscience. The idea is this: you make a stimulus larger and larger and larger. Imagine that the receptive field of the neuron is maybe this size, okay? And it likes vertical. Once you make the stimulus fill the receptive field, you get a big, nice response. But once you go beyond the size of the receptive field, you start entering some regions that somehow, people are still debating how, they create some form of suppression. So these curves have been published for a long time, and this phenomenon has had many names. Hubel and Wiesel discovered it in 1965, and they called it hypercomplexity. Then it became known as end-stopping, then it became size tuning, then surround inhibition, and now it's called surround suppression. And this kind of curve has appeared all over the literature, and there's been lots of theory papers written about why this is good. And the idea is that if you have a large stimulus, too many neurons would fire at the same time, and your code would not be sparse, and by having surround suppression, you enforce sparseness in your code. And which is a beautiful paper asserting this. So we were very surprised to see that when an animal runs, in many cells, the surround suppression goes away. And which is, you know, well, two things happen. First of all, the overall mean firing rate goes up a little bit, and then clearly this curve is no longer going down with size, okay? This is a cell that shows the effect very strongly. Let me show you now a very dumb average across the population. This is a very dumb average, taking every cell without adjusting for preferred diameter or for anything. And 1 is the peak firing rate. And you can see that our average cell has a certain amount of size tuning, and when the animal runs, this whole curve goes up. But if you look at the effect of running for small stimuli, it's much smaller than the effect of running for large stimuli. So this curve decreases less than this curve. Surround suppression is reduced. By the way, the difference between these two curves is shown here, and you can see that it goes up. And another analysis you can do is you can take each neuron one by one and ask, what happened to its suppression index, which is the ratio of this to this, basically. And for all the cells that had a good suppression index when the animal was stationary, the suppression index got murdered by running, basically. So something is happening that is changing the way the neuron integrates space. And because I'm kind of fixated with this divisive model called normalization, we applied that model to these data. And this model is, in this case, applied to space. The model says that there is a receptive field that provides a drive to the denominator, and there is a suppressive field that is larger that provides suppression and enters the denominator, and the interaction between these two gives you size tuning. And then there's simply an additive term and a rectification term. And we asked, what do we need to change in this model to account for the effects? And we discovered that we had to allow two numbers to change. One was an additive term, which is shown here, which invariably goes up when the animal runs. And the other was we needed to change the gain of the divisive term, which often, not always, but very often goes down when the animal runs. So once again, okay, this is pure speculation, but I showed you that the effects of noise, to use Heim's term, in an anesthetized cat were both additive and multiplicative, and we have no idea where that noise came from because that cat was anesthetized. But if you now were doing this experiment here, and you didn't know whether the animal was running or not, you would call these differences between these points and these points, you would call them noise. And you would study it, and you would discover that the effect of this noise is both additive and multiplicative, right? So it's possible that this running is one of the ways in which the inputs come to V1 and cause additive and multiplicative effects. And if you don't measure them, you'll call them noise. If you can measure them, you'll call them non-visual inputs to V1.
So the scenario is that sometimes it's running, sometimes it's not, and you don't know.
Well, when it's anesthetized, it's something else.
I wouldn't call it noise otherwise.
Yeah, of course. Yes.
If I know that it's
right.
If I average running,
yeah.
I won't call it different.
I know, but imagine that there was something that you don't know. How much the mouse is clenching its fist. Yeah. And my feeling is that pretty much all of the variability will be explained by something like that. Okay, so the summary here is that locomotion profoundly alters spatial integration in V1, reducing surround suppression, and it reduces the normalization signals. Okay. So what I'd like to do now is to move to a slightly less artificial situation. The mouse that you saw was walking. Yes?
There is one question about the control of this, because the mouse is running.
Yeah.
Now the eyes are...
Yes, the eyes.
So you get
okay, so the eyes. The eyes of the mouse don't move nearly as much as ours. We move our eyes about 3 times a second. They move them about once every 3 seconds. And when they are head fixed, they move their eyes only on the horizontal plane. It's possible that when they're not head fixed, they actually move them in more interesting ways, but we're grateful to them for moving them as little as possible, so it's fine with us. And they move by about 6 degrees on average, and so we don't worry about these movements. We do measure them. We don't worry about them for 2 reasons. The first is that eye movements would give you the opposite effect. You would have the one more thing I need to tell you is that when the animal runs, it moves its eyes a little more. Okay? Maybe it's just because it's more alert. And so the good news is that this artifact would give you the opposite result, because it would mean that the effect of running would be strongest on small stimuli, which can go in and out of the receptive field with eye movements, and it would be weakest with large stimuli, which can never go out of the receptive field with an eye movement. So that's a reason not to be worried. And another reason not to be worried is that we repeated this whole analysis considering only times when the eyes didn't move, and the story is the same. The data are uglier, though, because there's less data. Okay. So now, the example I showed you is one in which the animal runs, and the world moves in a completely unrelated way, which is not very natural. So let's move to a situation where the animal runs and the world moves consistently with it. It's still not a real virtual reality, well-done virtual reality, because you might have noticed that at some point the animal kind of went diagonally, and the world kept on going straight. We're up to this point, but not in the next section of the talk, which will be the last. We are ignoring 2 of the 3 degrees of freedom. The mouse can, on the ball, can translate this way, and rotate. There are 3 degrees of freedom. We're literally ignoring 2 of them. We're only considering this degree of freedom. So the animal really, all the animal can do is run faster, run slower, stop, and go a little backwards, which they tend to do when they scratch their back. And so now the question is, what happens in primary visual cortex when the animal runs in this environment? Notice that there's a grating, another grating, more like zebra crossing, a plaid, and another grating. And this is a homage to Tony Mopson, where I did my PhD. We placed some plaids and gratings in there. And so what you can imagine that happens is that in primary visual cortex, if a neuron is looking here, for example, and a big grating goes by or a plaid goes by, that neuron will fire more because there's contrast there. And in fact, that's exactly what we see. So this is the firing rate of a typical V1 neuron. We have lots more in the paper. And red means firing a lot, and blue means firing very little. And we're plotting the responses as a function of position in that corridor, where L1, L2, L3, and L4 are the landmarks, the gratings. I think it's grating, grating, plaid, grating. And we're also plotting them as a function of speed of the animal, okay? And so what you can see is that this neuron clearly fired more when this landmark went by. This is averaged over many runs through that environment, because in one run you can only be in a certain trajectory in the space, right? You cannot fill it. To fill it, you need to do multiple runs. So clearly, position matters. There's no question. But you will also notice that speed matters. And now you can wonder, so this particular neuron fires more the faster the animal goes. Now you can wonder, is this the speed at which the visual world moves? Because after all, this is a visual neuron. Or is this the speed at which the animal is running? And because this is properly done virtual reality, the 2 are identical. So what we need to do to answer this question is make bad virtual reality, so break it. So what happens is that we're going to do what's called open loop virtual reality, in which we simply play back to the mouse some videos that the mouse created by running in the virtual reality. So roughly speaking, imagine that the mouse goes 20 times through virtual reality, in virtual reality that is done properly. And so the faster the mouse goes, the faster the world moves. Then we play back those 20 movies, and we don't care for what the mouse does. Sometimes the mouse will run, so this is environment speed, this is run speed. Sometimes the mouse will run very fast, but it was a moment in the movie when the environment wasn't moving fast at all. Sometimes the movie is moving very fast, but the mouse is still. Sometimes they're both moving very fast. So we're exploring this space. These are trajectories that a mouse can take in one of these movies. In this particular case, there's not many trajectories in the middle, but this is not common. And the thing that I want to remind you is that in proper virtual reality, the mouse is always on this line, because it's proper virtual reality. Just like the faster I move, the faster the world moves back. Now we can ask, what happens to neurons in V1 Do they care for the environment speed, which would be what you would expect from vision? Do they care for running speed, which you might already suspect because I told you that locomotion has an effect on them? Or do they care for combinations of the two? Or do they even care for differences between them, right? Because there's an influential theory that you have a cortex to detect differences between what you see or what you experience and what you should experience. Right? Predictive coding. So there's various views of this. So let me show you what 3 cells in V1 do in that space. Here is a cell that cares only for environment speed. Red means a lot, blue means little. So the activity grows with visual speed, basically, the environment speed. And this neuron does not care about the running speed. It's pretty flat. Okay? This neuron here, instead, seems to care only for the running speed. You have a curve going up. It doesn't seem to care at all for the visual environment speed. This neuron here seems to combine the two. It responds the most when both are high. Okay? And I want to tell you, this is the most common observations, and to quantify it, we use a thing that I hesitate to call a model. It's just a description, really, of what's the angle of this. And so clearly, this is almost vertical. We'll call this pi over 16. It's almost 0. This is basically 45 degrees. We'll call it pi over 4. And this is horizontal. We'll call it pi over half. And now we have a number for each cell, and I can tell you which of these behaviors is most common. And what you see is that pi over 4, which is this one, is very much the most common. That's one that gives equal weight. It's not equal speed, but it gives equal weight to the two speeds, to running speed and to environment speed. So this is what you would have expected from a purely visual cortex that cares only for vision. All the cells should have done this, which is only care for visual speed. This is what you would have expected from a motor cortex that cares only for run speed and doesn't care for anything else. This is what most cells do, and this is one cell out of I don't know how many that showed any evidence for mismatch. So I don't think this is good news for the predictive coding theory, but we disagree on this with this other study who found different results, and we have different methods, and I'm happy to take questions about this, but not right now. But so in the summary of this bit of research is that in our hands, the way we do this experiment, most neurons in V1 seem to give equal weight to how fast the visual world is moving and how fast the animal is moving. We don't know where the signals for how fast the animal is moving is coming. For example, the whiskers touch the floor when the mouse runs. Maybe it's coming from the somatosensation. Maybe it's coming from the motor system. After all, it's the mouse that runs. It decides to run. We don't know if the weight would be different if one of the two signals was noisier. For example, in a Bayesian sense, you might imagine that you may want to give more weight to the running signal if you're in fog or if there's no light. And you may want to give more weight to the visual signal if you're skating on ice, and so on. So we don't know that. But in these conditions, in this environment, the neurons in V1 seem to integrate these two cues with equal weight.
So related to the last comment, in this experiment, the visual input most of the time provide salient information about the velocity, or a situation where not much is happening because there's no cue that's flowing by?
Most of the time there is a cue. Most of the time there's this noise on the wall that is always moving. See? So it's lower contrast, but it's always there. And we have other versions of this experiment in which the animal needs to lick in a certain place, and we know that they can do that very well. So they form a concept of space, and the hippocampus makes place fields there. So it's a place for them.
Yes. About this single mismatch. So how much of the experiment was actually a mismatch of velocity? You're moving forward, and the movie was actually moving back.
Good point. Good point. There's never mismatch in which things go backwards. There's mismatch in the sense that you're moving and the movie is not moving, or the world is not moving, or the other way around. So I feel dragged into the distinction with this study, and I refuse to get there until the end of the talk. Okay, fine. It will happen at the end of the talk. So the summary here is that during navigation, locomotion modulates V1's analysis of visual motion. And okay, this sentence would have been anathema to Hubel and Wiesel. What? You know, the animal walks, and the way V1 analyzes moving stimuli now is different. So this is considered normal in 2016, but it would not have been considered normal 10 years ago. And then the other thing that we find is that most V1 neurons weigh run speed and environment speed equally. We will surely get back to this because I can see that there are questions. But I do want to get to the last bit of my talk, which is much newer, unpublished, and it's work that takes us a bit beyond primary visual cortex, and actually possibly beyond visual cortex. So let me explain what I'm showing you here. These are outlines of a few visual areas. This is V1, this is LM, and I forget these names, but also one of the reasons why I forget these names is that they are nonsensical. So LM means lateral medial. I rest my case. Okay, okay, so they call it AM, PM, whatever. But anyway, so these are the ones that we can map with retinotopy, and I actually showed you the movie that gave rise to this. We take a mouse, we image. Usually, we try to image as much as we can of one hemisphere. But for two-photon microscopy, we may put a window that is maybe 5 millimeters in diameter. This is 1 millimeter, so maybe it's 1, 2, 3, 4. Maybe 4 millimeters actually in diameter, 4 or 5. So we will take an area like this, where this is visual, this is somatosensory, this is auditory, not primary auditory, okay? Because the primary auditory would be down. This is probably secondary auditory. And so what's between these areas? This is a slightly older 2012 atlas. Don't buy at all the names of the visual areas. They're completely random here, I think. But consider that blue means visual. Green means somatosensory. This is actually the barrel field because we measure the responses to whiskers. And between the green and the blue lies this purple. And this purple is parietal cortex, which in humans and in primates in general is huge and does all sorts of interesting things. I was talking about it today, about neglect and other things. And so we're interested in knowing what happens here during various situations. And so the reason why we're interested is that we want to go now beyond simple navigation, which is what I showed you before, if you can call traversing a corridor navigation. And we want to now understand more about what happens in visual cortex and in parietal cortex during a more natural situation, which is you make decisions about navigation. Let me go here, let me go there. Okay? So this is why we moved we want to image not only here but also here. And there's a large literature about what parietal cortex does in rodents. Slide told you that we're trying to go back and forth along this line, and I've already spent 2 hours in this room telling you about it, and I'm happy to stop boring you with it, but I gave you examples in which we can more and more control what the behavior is, or at least measure it, and when we do that, we understand more and more of what individual neurons do, and that I think is a reassuring fact. And so the overall summary of the whole talk is this. If you go to LGN, its responses can be predicted fairly well, but just simple concepts, filtering, gain control. If you go to V1, yeah, if you use simple stimuli, you can predict them too, for example, with the normalization model, but only if you use simple stimuli and if you average over a ton of presentations, because V1 responses are way more variable, that is less visual than LGN responses. Variability is shared across the population and is both additive and multiplicative. One of the non-visual factors that determines V1 activity is something motor, such as locomotion. And it has a profound impact on V1. It changes its ability to integrate over space. But during navigation, locomotion not only changes receptive fields, basically, but it also modulates its analysis of visual motion, of primary visual cortex. And if you go beyond V1, parietal neurons seem to encode combinations of where you are and where you're headed. And I think we end with good news, which is if you have a good model, you can predict what neurons far into the brain are doing on a trial-by-trial basis. And I just want to end there and really thank you for your patience, because you've heard my voice for more than is warranted. Thank you so much.
About the first part of your talk with the key control and division normalization, so can you say a bit more maybe about the biological substrate or implementation of normalization in game control? Because in one case you put a denominator in a model, but what really happened on the neural?
I know. Yeah, I agree. For example, if normalization was involved in some for neurological disease, you can't go to a pharmacist and say, hey, can you get me something from a denominator? Right? So no, I completely agree. So, first of all, normalization seems to be a widespread computation that takes place in various species, from Drosophila olfactory system to maybe the computation of value in human parietal cortex. And it's very clear to me, and I think many will agree, that it's done differently in different systems. So in systems that are very feed-forward, like the olfactory system of Drosophila, normalization is done through inhibition. You literally have an inhibitory neuron that provides a denominator. Okay? And Rachel Wilson has beautiful studies on this. But if you go to the cortex, which is much more recurrently connected, I thought that the normalization would operate through inhibition, but in fact, the more I study it, the more I see that inhibition has very little to do with it. It has a lot to do with excitation. So neurons reduce their activity because they receive less recurrent excitation. And so even the word suppression is wrong. One shouldn't think of the neurons responding less to big stimuli because they're being suppressed. One should think of them as responding more to small stimuli because they're being excited. So I believe that in cortex, normalization is due to recurrent circuits, and Haim had models of this kind, and there's various models, and actually Misha Tzaduk's had a model that goes in that direction, and Ken Miller has models of that kind, where really what drives the neurons is recurrent excitation. And when you do anything that will take that away, responses go down. So if I were to start again, in cortex, I wouldn't have used an equation with division. I would have used an equation with multiplication. And I would have said, what's making that multiplier bigger or smaller? Not what's making that denominator bigger or smaller. Of course, mathematically it's the same thing, but conceptually it would have really helped me to think that way. And to be fair, people like Rodney Douglas and Kevin Martin, they've been thinking that way for a long time.
Yes,
Sure,
yes,
Students first.
Okay.
So you showed that there are some neurons that encode in visual cortex that encode the motor activity,
Yeah.
which probably implies that they get inputs from the motor cortex.
Okay, no, that's not necessarily true. Because first of all, the whiskers touch the ground when an animal runs. So you could imagine inputs coming from a somatosensory system. Second, you could imagine that running more just means, I actually don't believe what I'm saying now, but it's a possibility, that running more means you're more aroused and just you have more of, say, acetylcholine in your brain. So there's various ways in which those signals could get to V1, not necessarily from motor cortex. Does that make sense?
Yes.
Okay.
I wondered if you would expect to see the mismatch between the visual field and the speed of the mouse, and maybe some higher regions that initially project this as visual field.
Oh, I don't know. Should I get into the reason why we don't see mismatch and that other team sees mismatch? I can in a couple minutes. Okay, so in our experiment, the animal is in a world that makes sense for 20 runs. And then for 20 runs, the animal is in a world that makes no sense. Because if they run fast, the world might be not moving and vice versa. We think that it's an okay design. The group by Keller et al., they use a very different design. Their mouse runs, and occasionally the world stops or goes backwards. Okay, very transiently. And in those circumstances, they find neurons that seem sensitive to mismatch. I am skeptical of that design because I think these kind of abrupt changes would create a signal throughout the brain that says, whoa, what's going on? They are skeptical of our design because they say, well, maybe you do have a system for mismatch, but you can turn it off. And maybe the mouse, when it's doing 20 runs in a world that makes no sense, just simply turns off its system for mismatch, the same way that you would turn it off when you're driving a car, right? Because you're not walking, the world is moving, so clearly you can turn off that system, right? So I think both of us have views, and the way to do it would be one of the two groups would run the experiment the way the other group ran it. And we're not doing it, they're not doing it, so we're remaining there.
So if I'm allowed to have a comment here, you can just go the experiments that use like visual rotation or force fields or motor system, and you can have the expected world running.
Mm-hmm.
From time to time you have a catch trial when the expected world turns off and then comes back.
Yeah.
And then all the problems that
It's an intermediate design then. That's another way to do it. Do a design that is intermediate. Yeah, sorry, there was a question.
You answered it.
I answered it, okay.
Matteo, it's true that we're 10 million years closer to mice than we are to cats.
Speak for yourself.
Many of us are. But mice really are nocturnal animals and have a very different lifestyle than we do. And
I agree with the second statement, not the first. They're not nocturnal.
If you look at their subcortical visual system compared to the amount of cortex they have, there's a lot more subcortical than there's cortical.
Okay.
To move from cats to mice, I wonder. My question is the behavioral task, seeing a grading on the right and then turning right. Are you sure that can't be done without a cortex?
Okay, great, fantastic. So a number of statements. First of all, I have to say that a lot of the things I talked about today, I have no idea whether they extend to cousins of ours that are closer, like primates. And it's quite possible that they don't. Okay. This said, I have to first react to the idea that mice are nocturnal. From a person who studies vision, an animal is nocturnal if it has a tapetum. If it doesn't have a tapetum, which is the reflective thing that a cat has, the thing that shines when you point your car to it, an animal is barely considered nocturnal. And in fact, there was a study done in which a bunch of lab mice were put in the wild in Russia. I don't know why Russia. But they were protected from animals, from predators with a big net. And so they studied the activity of a lot of mice together. And what is true is that the diurnal and nocturnal activities are very related to each other, just like yours and your mate probably at home are, right? But they all drifted. They weren't necessarily nocturnal or diurnal. It has to do with the availability of food, with temperature, with the predators, but a mouse is not necessarily a nocturnal animal. And it has rods and cones. It doesn't really have the visual system of a nocturnal animal. This said, yes, it probably does a lot more with its superior colliculus relative to cortex than we do. I will agree with that. And some of these tasks, though, are very impaired by optogenetic inactivations of visual cortex, specifically one that I didn't show today. This one is mildly impaired by
Just mildly impaired.
yeah.
So he can still turn right even if if visual cortex is off, turned off.
Yes, but we didn't turn off the whole visual cortex, and one side of it is always good. We never did it bilaterally. Well, yes and no, in the sense that you can do the task with just one eye, right? Just looking at one side. If the grating is on that side, good, go that way. If it's not, go the other way.
Better try turning off both cancers then.
Yes, but I'm not trying to prove a first of all, in tasks where we are trying to prove a causality between activity of visual cortex and behavior, we certainly do that, and we see massive effects. And these are tasks in which you need to detect the presence of a contrast and discriminate between two contrasts. But in this task, for now, we're simply trying to understand what are these neurons doing. We're not trying to say, how are these neurons telling the mouse what to do. We're just simply, for now, trying to understand what are these neurons doing. It's a complicated situation, but very realistic. And understanding what they do, I think, is an important step. From there to say, the mouse went right because these neurons told it to go right, that would be wonderful. But I don't think it's a necessity in this study.
When the mouse is running,
Yeah.
that make the
Yeah.
Is that the input from another network? I mean, is dopamine, is hippocampus, or have you ever tried to make this experiment of the T decision, but with the antagonist of T1?
Okay, so I can tell you what theories are there, but I don't think that they work. The dominant theory is that there's more acetylcholine. Acetylcholine drives VIP positive interneurons. VIP positive interneurons suppress somatostatin interneurons. Somatostatin neurons used to suppress excitatory neurons, but because now they're suppressed, they no longer do so, and therefore excitatory neurons go up. It's called the disynaptic inhibitory hypothesis. And it also comes from the lab of Stryker. It does not agree with data that we're acquiring now with two-photon imaging during running. That's all I know about this stuff.
All right. Thank you.
Thank you for your patience. Thank you.
First of all, we had a lovely visit. And second, this is the past by now.
Yes.
This moment. And when you try to examine the responses, my question in the middle of the talk was, how would the activity now predict the activity in the future? Whether you go from parietal to visual and the opposite, right, in the two directions. What is your two directions? I missed a little bit the time.
Yeah, everything is always in the present.
Okay,
True.
so this is yet another thing. And I mention it because we have future, and the future is that next week there are many events basically involving in several places in Jerusalem. It's the Brain Awareness Week. So we have Cinematheque, we have Mazia House, etc. Please look at the website and attend.